Welcome to my presentation. Today we are going to see the procedure for designing flange coupling. Here I am giving the step-by-step procedure for flange coupling design. Before going to the presentation, I want to discuss about the parts involved in the flange coupling design. If you see this flange coupling diagram, we are having a shaft, hub, key, then flange, another one is bolt. So we have 5 components in this flange coupling setup. So as we know that the coupling is used to connect 2 different shafts to transmit the power. That was the main objective to use flange coupling. So first step, we have to design the shaft. That means we have to find the diameter. For the suitable diameter, we are going to select the flange coupling. So for that, power formula we have to use, that is 2 pi nt by 60. Generally, whenever we consider the shaft, so we should know how much power it is going to transmit and how much RPM it is going to be rotated. So that will be always given as an input for any problem. So if they are given power and speed, we can find the torque. Whenever we are going to find the torque from the power formula, that will be mean torque or full torque or maximum torque. If there is a service factor is given, then Tmax is not going to be a Tmean and it's not equal to full torque. So for that case, we have to use the maximum torque is equal to service factor into mean torque. After find the torque, we have to use the torque value here to find the diameter. 5 by 16 FSTQ. This formula can be found from the PSG data book, page 7.21. After finding the diameter of the particular shaft, we have to select the standard diameter. For that, we have to move to the design data book, the page number 7.20. Here we are having a basic series of preferred numbers. We are having a various series R5, R10, and R20 and R40. Based on the accuracy level, what we are expecting, so we can use series. Most of the cases, the people are using R20 series as a common method. So I am choosing this R20 series. So from this, we have to choose the next value of your calculated value from this R20 series. That was a standard diameter for the shaft during design of dimension of shaft. The next, after finding the diameter, we are going to find the proportion. That means other dimensions of other component corresponding to the diameter of the shaft. There are 2 methods. Method 1, which is purely taken from the PhD data book for diameter value. Just I want to show that one. If you come back again, 7.106. Here 7.107 we are having a table. There they have given the proportion of forced end rigid couplings. If you see in the table 1, they are giving the coupling number and the safe shaft diameter, the maximum and minimum is. So whatever the value we are getting in between these two range, then we have to choose this dimension. So the D1 is nothing but flange diameter. B is nothing but thickness of the flange. And D3 is nothing but pitch circle diameter. If you see in this diagram, we can see that here they are written. This is the outside diameter of the flange, that is D1, which is mentioned in the design data book. And B is nothing but thickness of the flange. Here they have given TF. And if you come back the pitch circle diameter, that is D, PCD we can call. And the hub diameter here, D3 is a hub diameter. And T2 is the pitch circle diameter. And if you come to D1, it is a bolt diameter. The N is number of bolt according to your diameter of the shaft. This is one method. If you go proportion relevant to the diameter, which is not available in the design data book. So we have to remember this. If I am taking this flange diameter, that is become a 4 into diameter of shaft. Thickness of the flange 0.5D and pitch circle diameter is 3D. Hub diameter 2D. Number of bolt corresponding to your diameter range, we have to choose that number of bolt 4, 6 or 8. And the length of the key or hub is going to be 1.5D. These are the proportions we have to take before going for actual design of other components of the flange couple. The step 3. So after completing the shaft and we are going for the next component, hub. The hub is connected with the shaft. So we are going to the hub design. Hub is hollow shaft. So we are taking the hollow shaft formula to find the standard or working shear stress for the hub. So here the torque is equal to 5 by 16 shear stress of hub and outer diameter of hub power 4 minus inner diameter of hub power 4 divided by outer diameter. Outer diameter is equal to T2 that we have already taken as a 2D in another method 2 and this is from data book. And Di is nothing but internal diameter of the hub that is equal to the diameter of the shaft because the shaft is placed or seated on the internal diameter of the hub. So from this formula, so we are going to find out the shear stress for the hub and whether this hub diameter, hub shear stress is less than the maximum or permissible shear stress value, which generally used to give in the given data. If your value, calculated value, is lesser than the design, then your design is safe. Step 4, key design. So next component is key. So here we have considered as a rectangular key. So I have taken this dimension. So first for the key, we have already found the length of the key. Now we are going to find the width and the height, we can call thickness of the key. That we are going to take from PH data 5.16. That I will show that now. So this is the page to find the width and the height of the key. If you see the range of diameter is given here. So 6 to 8, 8 to 10, 10 to 12. These are the range of diameter. Accordingly, you have to find out the width and the height of the key. Example, if you are having the diameter of shaft is 35, so that 30 and 38, the range which is for 35 mm diameter, then we can choose this width of the key is 10 and the height of the key is 8. So the same way, whatever the data value, diameter value you are getting, accordingly you can choose this width and the height of the. The next, after find the dimension, as a design engineer, we have to confirm whether that particular dimension is going to withstand the load. So there are two cases in the case of key. The first case is shear stress and another one is crushing stress. If you see in the diagram I have discussed here, this is actually diagram for the key design. So if you take this a key, when the load is acting on the key, that particular rectangular key is sheared. That means splitted into two. So where that shearing is happened, that area is called as shearing area. So that shearing area is given here L into B. And when the load is acting, that the key is subjected by the crushing stress, then area going to be length and the thickness by 2. It is half of the thickness. So we have given L into H by 2. So this formula, this area formula we are going to use in the checking procedure. Now if you see, checking for shear stress, we are taking the formula T max is equal to shear area into shear stress into the radius. So we know that torque is nothing but force into radius. So force is here, area into stress, and the radius is nothing but diameter by 2. So after finding this shear stress, whether the calculated shear stress is lesser than the maximum shear stress, that we have to confirm. If that is assumed, then we can call as design is safe. Then maximum stress for the crushing condition. So we have taken T max is equal to the crushing area into crushing stress into radius. So from this, the same procedure we are following. We are finding the shear stress, whether it is less or higher than the maximum stress. We are comparing. If it is less, then design is safe. Then we are moving to the bolt design. Bolt design. First, we have to find the diameter of the bolt, which was not calculated from the method 1 and method 2. So that calculation we have to do now. For that, so I am taking T max equal to pi by 4 dB squared into tau b into number of bolts into T2 by 2. That is pitch circle diameter divided by 2. From this, we can find the diameter of the bolt. By using the shear condition, we are finding the diameter of the bolt. But anyway, for any dimension, we need to check the capacity of the particular component. So we are taking the diameter value, whether it suit for the application or not, by checking compressive stress of the bolt. For that, I have taken this formula, T max N into diameter of the bolt into thickness and sigma CB into PCD. How I have got this formula? If you see this diagram, is only portion of the bolt and the flange is given here. So this is the actual setup. After that shearing, the bolt is become like this. So only the shearing area for that particular bolt setup, it is single shear. So we are using the shear area is pi by 4 D1 squared. If you take the crushing condition, so where the crushing exactly is acting on bolt, that is AC is equal to TF into diameter of the bolt. So that we have given here. That means number of bolt, how much we are using into area, then stress into diameter by 2, that is radius. From this, we are confirming that whatever the bolt diameter we have found, it was suited for the application. Next, the flange design. For that, we have already found the flange dimension, that was flange diameter and thickness of the flange. So both dimensions already we have found. So we have to confirm that whether that dimension is going to be withstand the particular stress. So here we are considering this shear stress checking. So T max equal to pi into D3 squared by 2 into tau F into TF. So now we can raise a question how I got this. That area which was given here, pi by 2 into D3 squared. So we will confirm it. So if you see this diagram, this was actually flange and hub setup. If you see this hub portion, there was a shearing failure. So the shearing failure is going to be surface area of the particular hub where the hub and flange is joining. pi d3 into thickness. So that formula I am substituting here for the area and into tau f into diameter by 2. After we do this calculation, we will get pi into d3 squared by 2 into shear stress into thickness of the flange. From this calculation, we have to confirm that whether that shear stress is going to be less than the maximum or given permissible value. Then the design is safe. So this is the procedure of flange coupling. So very important thing what we have discussed in flange coupling design. We are finding the dimension. Then we are checking whether the dimension is suitable for the particular application of load. So dimension and checking. These are the procedure for any component of design